started last class. So, as we have seen so many applications while conducting the practicals based on MLR, right? How this heteroscedasticity works. We have seen the different plots. Even using plots also we have identified whether the heteroscedasticity exists or not. Or using some test like BP test we have used to analyze whether the heteroscedasticity exists in the data or not. So in all the cases we have seen whether how the this particular heteroscedasticity exists. So actual meaning of heteroscedasticity means we are generally dealing with the variance. Okay, generally dealing with the variance. Is the variance is same among the data? Okay. It's like when you go for like uh, checking for like two treatments and you want to just check whether the variance is same among these two treatments or not. Okay, so one can check the heteroscedasticity using the concepts of like using BP test, or I have given another test like I can say there are two method I can say detection. One will be the Bush Pagan Godfrey test, another one with the Spearman rank correlation. So I think Spearman rank correlation test it is not there in your syllabus because it is very simple, which I think that we have already seen in the FIBSC level. That is like Spearman rank correlation, but that sometimes fails because of unavailability of data and other reasons. But generally, the test which we are using in your syllabus, which is Bush, maybe sometime it is E or sometime A. Bush, I think it is something like that. So Bush Pagan Godfrey test. So we will discuss more about this Bush Pagan Godfrey test in I think in Notepad. We are just so we can see this derivation part. So what this derivation part says in the Notepad, I think you're able to see the Notepad also. So this basically this Bush Pagan test is generally to be checked for the like if you want to check whether heteroscedasticity exists or not, one may go for Bush Pagan Godfrey test. So what this uh, Bush Pagan Godfrey test says when we have the data like uh, whether we have a data like just write down the spelling of that first, then we can start. It is U. This is A. U. Bush Pagan Godfrey test. So in bracket I can say sometime it is also termed as Bipri test. You should familiar with the term. Now what this basically Bush Pagan test says, this test is applied when we are discussing more about the heteroscedasticity. So if you wanted to check whether the I can say in my variable or in my data whether the variance is equal or generally you are already knowing that when we apply ANOVA or any other technique, we do not directly go to the applying like different treatments. There are some basic assumptions. Okay, so before applying ANOVA, we must check the variance is same or not. We must check the variances. See, analysis of variance means you are actually you are interested on the variance part. So you are assuming that the variances is same and you are comparing their mean. Okay. So for that purpose, we need to check for the heteroscedasticity. So one may go for the heteroscedasticity and using in MLR also. So I can say Basically, this test is used to detect, just a minute. So this test is used to detect heteroscedasticity. It is hanged, I think. Just a minute. Heteroscedasticity. Heteroscedasticity. So it is used to detect the heteroscedasticity in linear regression models. Now let's consider K explanatory model. So we have a K explanatory model, or I can say K explanatory variables regression model. So I think everybody is knowing what is the K explanatory regression model. So I will say yi is equal to, it's a beta naught plus beta 1 x 1 I plus beta 2 x 2 I and so on, plus beta k x k I plus we have ei or ui, whatever the grad term we are assuming. And what is the basic assumption here? Assume that assume that the variance error variance sigma I square is a linear is a linear function linear function of z, where these z's are sum or all of x. Means I can say this x, the error term which we are assuming, error variance which we are assuming sigma square, that is a function of all z's. Okay, all z's, and these z's may be some functions of x. It may be some or it may be all. It may be some or it may be all. All of the x. That is therefore sigma I square. So I'm saying this variance, this error variance, error variance is what? It's a linear function. It's a linear function of z. So I'm just trying to make this variance, particular variance is a linear function. It's a linear function. So my linear function is this. Let's say alpha naught plus alpha 1 z 1 I plus alpha 2 z 2 I and so on, alpha k z k I plus, I think there is nothing plus because there is no error term, because we are assuming that is the function, that is the function. So you can just read this statement, assuming that the error variance sigma I square is a linear function, very important, linear function of zs. So this is my linear function. Okay, and then further here here sorry, here, if the model is homoscedasticity, homoscedastic 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 homoscedastic. Okay, so you have to just read it, pronounce it properly. Okay, so just do it twice, like take half pronounce, so you can get it better. Homoscedastic. So if it is same, if the variance is same, then I may say that sigma I square is equal to alpha naught and and alpha 1 alpha 2 so on, alpha k is equal to 0. So if the model is homoscedastic, then sigma I square become is equal to, because it is going to be same na, constant hoga आपका. It is going to be constant, and remaining this sigma alpha 1 alpha 2 alpha k all are going to be 0. Therefore now what happened, to check homoscedasticity, homoscedasticity homoscedasticity, we test the hypothesis that that alpha 1 is equal to alpha 2 is equal to alpha k is equal to 0. So if this all alphas are equal to 0, that means your data is homoscedasticity. But if alphas are not equal to 0, I may say that the data is heteroscedastic. So you remember that these concepts are very important. These concepts are very important. So now we'll go to test procedure. We'll go to the test procedure. So what this test procedure says, since we have the, I can say we have testing, so obviously we have a test procedure. So what test procedure says, we need to obtain the OLS. Obviously, we need to obtain their estimates. Then only we can go ahead. OLS estimators of the parameter of the parameters of k explanatory variable, k explanatory variables, linear regression model, and find EI. Find EI. Okay. So once you estimate the parameter, I hope you can obtain the EI. Once you obtain EI, obtain the maximum likelihood function. I hope you are already knowing what is this maximum likelihood function, likelihood estimator, I can say, likelihood estimator of sigma square, and it is given by sigma hat square is equal to summation ei square upon n. And now defining pi, that is your parentage, which is ei square upon sigma hat square. So this sigma hat square you can calculate from here, and this EI will be the individual because you need to check for all PIs. You need to check for all PIs. Okay. So for that purpose, you need to check for P1, P2, so on. Now consider a regression model, linear regression model of P on Z1, Z2, and so on Zm. So I'm considering, so here if you just see the Z values like this one, Z1, Z2, Zm, it is given by it is given by it is given by Pi is equal to alpha naught plus alpha 1 Z 1 I, alpha 2 Z 2 I, so on alpha m Z m I plus Vi term. And what is this Vi? This Vi is the residual, that is the error term, residual term of this model. Now obtain explained sum of squares, which generally called ESS. Here ESS is equal to alpha hat square into summation of Z I square. And basically now your testing part comes here. There is no heteroscedasticity. There is no heteroscedasticity. heteroscedasticity versus H1 not H1. And now I'm defining here my test statistics. Test statistics. What is my test statistics? It is chi-square calculated is equal to ESS upon 2 follows chi-square with m degree, and this is for large sample. For large sample, and what could be decision criterion? Decision criterion, reject H naught, reject H naught if chi-square calculated will be greater than chi-square m comma alpha degree of freedom, and conclude that conclude that so if you are rejecting H naught, that means you are concluding that there is there is heteroscedasticity in the model. So with this your test procedure is over. See, it is not very difficult, I think. You have to just think of little bit in different sense. So this is the model. This is the model. And if we assume this variances is a some function of your z, and where z will be some, that z may be some x or all x. This z may be some x or all x. And if there will be no heteroscedasticity, then these all z's are equal. Z's are going to be 0. That means your alphas are equal to 0. If all alphas are equal to 0, that means automatically your variance is equal to constant value. But if there is a like to check, I think it is a homoscedasticity or heteroscedasticity. Let me just check this. So to check for homoscedasticity, we need to test whether all alphas are equal to 0. We have to check for all alphas are equal to 0. If all alphas are not equal to 0, then I will say it is heteroscedasticity. But if it is all equal to 0, that means there is a homoscedasticity. So what is test procedure? See, we have to just estimate all parameter, and once you get the parameter, one can able to get the values of EI. One can get using MLE estimator, which I think you have already seen how to get this MLE estimators. Once you have this sigma hat square, one can define PI, which is EI square upon sigma hat square, correct? And then you consider that function, and this variances, the variances which you have defined, this is equal to your PI. Therefore, PI is equal to alpha naught, alpha 1 z1, alpha 2 z2, so on, alpha zm, and plus there is error term now, because it may happen while calculating you may get some error, and that PI is residual sum of square. And once you obtain that, one can obtain the ESS using this formula, alpha 1 alpha 1 hat square into summation of zi square. Now what is the testing part? H naught versus H1. That is there is a homoscedasticity. There is no heteroscedasticity means, that means homoscedasticity versus heteroscedasticity. ESS upon 2. So whenever we are interested to obtain chi-square calculated value, we have to always define ESS by 2, and which follows chi-square with m degree of freedom, and this is for large sample. This is for large sample. And criteria you already knowing. If the chi-square calculated greater than the chi-square tabulated, we may always go for like reject H naught. Reject H naught means that there is a heteroscedasticity present in the data. So this is the whole procedure when there is exist like when you want to check like there is a homoscedasticity exist or not. Okay, so that is the very important function which you have to always assume. Yes, any question? Let me see in the chat box. Why we are considering error variance is a linear function of z. See, you have to decide now whether there will be there may exist like some error or not. So we have to assume some function, then only you can able to find na variance, like, because that variances can be linear function of some variables na. That variance will be, it's a linear function of some variable which is contributed by your x only, which is contributed by x only, right? So that's why we need to create a sigma I square is a function which explains whether it is variable, whether the variances exist or not. So for that purpose we are creating the one linear function and we are checking whether it is homo or it is hetero. Yes, any other question? uh, what is z1 zi? See, this all zi's, it is a, it may be your x only. This all z1 z2, it, see, it is written here now, you can see z's are some or all of the x, means actually I can write x also, but it can be some function, it can be some function, like if you have x matrix maybe 3 cross 3, so it can be 2 cross 2 also. So z can be 2 cross 2 also, z can be 1 cross 1 also. So that's why it is told na, z's are some or all of the x. Are you getting? So again, this is the actual your observation only. This is actual your independent variables only. But it may assume all, it may assume some. So that's why they have written some or all. Yes. Any other question? Understand this test procedure clearly because that is very important. And one may, I think, can. So, for example, if we have that EI data, see, basically in your practical problem, there won't be given the manual problem, right? You don't have given the like big type of problem, but in theory it can be expected. Okay, so how the questions can be asked, for example, uh, what is your formula for test ess? It is something like ess upon 2, ess upon 2, right? And so you need to know how to find this ess, that is all important. Okay, so when you have given the data for like sigma, so you need to obtain sigma hat. सिग्मा हेट निकालना पड़ेगा आपको, तो सिग्मा हेट कैसे निकालोगे आप? सिग्मा हेट इज ई एस एस अपॉन ई आई स्क्वायर अपॉन एन। तो आपको ई आई का डेटा रहेगा और एक्स का डेटा रहेगा, दो डेटा आपको दिया रहेगा। तो ई आई का डेटा दिया तो यू कैन फाइंड ई आई स्क्वायर एंड यू कैन गेट समेशन डिवाइड बाय एन इज ऑलरेडी नोन, यू कैन कैलकुलेट दिस। once you calculate this, one can obtain pi for individual cases, right? हर एक के लिए आप pi निकाल सकते हैं। and once you get pi, I think you are already assuming zi is equal to x, zi is equal to xi. तो zi is equal to xi मतलब क्या हो गया? Sum of zi is nothing but sum of xi. Are you getting the point? And once you get that term, how do you calculate this sigma alpha 1? Or how you calculate alpha 1 hat? What is alpha 1 hat? Remember, alpha 1 hat, how you calculate alpha 1 hat? So if your model is only this much, or only this much portion, obviously including error term, only this much, plus vi term. So how do you calculate this alpha 1? So if you apply again regression concepts, and one can estimate this alpha 1 hat, right, using the OLS estimator. So alpha 1 hat can be obtained using formula summation zi pi upon summation zi square. I think this you have already computed. If you remember, beta 1 कैसे निकालते हो आप? Y on x, how you calculate? It is summation x into y into summation of x square, something like that. Okay. So your foundation should be very strong. You found, see, assume this pi will be your dependent variable and x will be your z will be your independent variable, and apply your OLS and we'll get the alpha 1. सी अभी आपको मॉडल पढ़ाया है y इज इक्वल टू बीटा नॉट प्लस बीटा 1 x 1, तो आप क्या है ना, वही रट्टा मारते हो? नहीं, वो रट्टा नहीं मारने का। अगर y में इज इक्वल टू पी आई लेता हूँ और x इज इक्वल टू मैं जेड आई लेता हूँ, व्हाट कुड बी माई मॉडल, व्हाट कुड बी माई एस्टिमेटर्स, हाउ डू वी कैलकुलेट? So that is all basically based on the conceptual. तो आपको वो सब आना चाहिए, और एक बार ये वैल्यू मिल गया आपको, अल्फा 1 मिल गया, तो ये से सब पॉइंट 2 करके कैलकुलेट करें। सो make sure that you may get the questions in your theory, maybe some type of like the problem is given, you need to calculate ESS. Okay, so just thorough with that all concepts, how it can be applied it in theory as well. Obviously in practical it is difficult to do it manually, but one may try out manually and just work on that. Okay. Yes, any question? How do you decide the test statistics? See, this test statistics is based on some criteria. How we decide, like if we are testing for the mean, how we decide x bar minus mean upon sigma upon root. How we decide that? Okay, so that is all. That is all. This because for the last sample, it is follows chi-square for the last, and you are comparing two variances, na? So if you are comparing two variances, so ratio of two variances follows what? F statistics, right? It is follows F statistics, and for the last sample, you can compare it is chi-square. So that's why it is coming chi-square. So if you just do ESS by 2, it follows chi-square. It follows. So this is all basically test statistics, which is we have to not actually decide. We have to just understand how it works. Otherwise, when you compare for the variances, so you know for checking variances, we apply. If you are comparing two variances, we use F test. Correct? We use F test. So comparing two main, we apply T test. Are you getting my point? Comparing like two independent variable, we apply chi-square. If you remember, like we have given marks of let's say marks in statistics, marks in mathematics. You want to check whether they are dependent or independent. Which test you want to apply? Which test you are going to decide? It is chi-square. Are you getting the point? It is going to be chi-square. That is all based on the your conceptual knowledge. कि कौन सा टेस्ट कैसे डिसाइड करना, that is all based on your like how much your concept is clear. Based on that you decide which test statistics can be applied. Yes, any other question? Okay, so this is the whole thing for the Bruce Pagan test. So that Bruce Pagan test is a very quite useful, and one may just work out this how this particular Bruce Pagan test works, and based on that one can apply that those tests, and that is very important. Now there may be some consequences of that Bruce test. Means there is some consequences exist in the due to heteroscedasticity. I think the consequence is not written here. It is something up down. Yeah. What happened? The consequences of using OLS estimators in the presence of heteroscedasticity. So whenever there is heteroscedasticity exists, what could be the consequences? So in the presence of OLS, in the presence of, I think this is nothing. It is not there. Presence of presence using OLS estimator obtain something is missing. I think this is something in presence of heteroscedasticity. This is in presence of heteroscedasticity, heteroscedasticity, comma OLS estimators obtained are unbiased and consistent, but again they are not more efficient. Again they are not more efficient. In other words, OLS estimators are not blue in the presence of heteroscedasticity. So you know what is the blue? We have seen already what is the concepts of blue. Correct? Therefore, T and F tests are based on these estimators can be highly misleading, and we may not get the correct answer. So since these estimators are not like very constant, I can say not blue in the presence of heteroscedasticity, one may get wrong results also while applying T or F. So that's why I think they have used for the chi-square. They went for the chi-square. So that concept you can just go through. And further, I think they have discussed. So what happened if like the test which is not giving uh, what's the consequence we have found? Then what we can do with that? How? What is the situation? How we can tackle that situation? If if there is a heteroscedasticity exists in the data, okay. See, once it is exist, like we cannot perform we cannot go ahead with the doing all setting models and everything, right? But for that purpose, we have WLS model, weighted least square estimators. We have weighted least square estimators, and if you just do little transformation in that weighted least square estimator, one may apply regression model. So how this weighted least square works? See, in presence of heteroscedasticity, OLS estimators are no more efficient. Like they don't have the minimum variance. So if they don't have the minimum variance, you may not apply ANOVA, right? So we estimate the weighted least square estimator, that is WLS estimator. तो हम लोग को क्या करना है? हम लोग नॉर्मल OLS नहीं estimators, नॉर्मल OLS अप्लाई करके हम लोग estimators निकाल देते, राइट? बट दैट टेक्निक फेल्स. तो जो अपने को बीटा नॉट बीटा वन मिलता है ना, that is that may be unbiased and consistent, but no longer it is efficient. Okay, so in that scenario one can estimate weighted least square estimate, and the usual ULS method is equivalent to weight assigned to each observation. So usual जो method हम लोग अप्लाई करते हैं हम लोग वही करेंगे, बट हम लोग उसको weight assume करके करेंगे. ठीक है, कैसे करेंगे वो सब देखेंगे. So since the heteroscedasticity variance something is, let me just go through that. Since in heteroscedasticity there may be some common. Let me just close it. Yeah, in heteroscedasticity, will be I think C something. Just correction here. Heteroscedasticity, comma variance is not constant, right? Since in heteroscedasticity the variance is not constant, so the knowledge of unequal variability observed in Y for different values of X should be used in such a manner that the observation with greater variability should less weight than less weight than those with the smaller variability. तो क्या होता है, जैसे कि हम लोग अगर मीन की बात करें, सिंपल टर्म, I'll talk in simple term. If you're talking about like the data, for example, let's say the weight, or let's say in our class only, height of height of all the students in our TYBSc classes, for example. So you may find that majority of all the heights like around, I will say it is 5.2 to 5.5 or 5.6. 5.2, I can say 5.1, 5.1 to 5.6, right? They are all basically, if I see the height of those students, there may be the I can say homoscedasticity will exist. But if there is such a height which is like 4.3, 4.2, and then 5.3, 5.3, 5.4, and there's somewhere 5.10, 5 point, again 10, 9, 10, 9. So you may see that there are few observations which is very higher, there are few observations which is lower, and there is normal. Okay, so if you try to see that concepts, your mean will be get fluctuated. Mean will be get fluctuated. So what the concept says here, if the variance is not constant, so the knowledge of unequal variability observed in y. So you may observe that there may be unequal variability. Means the variable will not, that variance is not same for all the values of x. तो इस सिचुएशन में क्या करना है हमको, यहाँ पे ग्रेटर वेरिएबिलिटी जो होता है, मतलब अगर मैं एक ऐसा वेट डिसाइड करता हूँ और वो वेट से अगर मैं पूरे डेटा को डिवाइड कर देता हूँ, तो मेरी जो ग्रेटर वेरिएबिलिटी है वो इक्विवेलेंट टू माय नॉर्मल वेरिएबिलिटी के पास में आ जाएगा, और जो स्मॉलर वेट है वो ऑटोमेटिक नॉर्मल हो जाएगा. ओके, that something transformation I have to use, then only I can able to make the data become a homoscedasticity, and one can go with the applying the models, and like regression model and ANOVA and everything can be applied. So that is the important concept you can always go through. Heteroscedasticity should be there. अगर होगा तो अनबायस्ड होगा. सी अगर हेटेरोस्केडास्टिक में क्या बोला आपको कि अगर जो एस्टिमेटर्स आप निकाले हैं, इट मे बी अनबायस्ड, इट मे बी कंसिस्टेंट, it may be unbiased, it may be consistent, but no longer it is going to be efficient. Means if you just add one more variable, trial and error, it may happen that their variance become the like larger and larger, since it is unbiased and consistent, right? Because of there is a heteroscedasticity present in the data. So that concept you can just when you just apply this maybe the heteroscedasticity or other thing that you can. I think there's one more practical is remaining, the like in weighted least square. So हम लोग weighted least square का practicals when we see ना, you become understand कि how is a particular thing will be work. So one can go with the weighted least square estimators. So how this weighted least square estimators works? So I mentioned we need to do certain transformation. We need to do certain transformation. Then only one can able to get more ideas about weighted least square estimators. Okay. So we have I can say weighted least square estimator. I can solve WLS estimator. So short form is WLS. So if you just consider the model, consider just a minute, I'll just because this line should be straight, otherwise while copying the things it maybe just cut the things. Okay, so we'll do the derivation based on OLS. So consider, again we consider one explanatory model. Consider one explanatory model, explanatory one explanatory variable regression model. This is something like looking very nice. Square estimators, WLS estimator. So consider one explanatory variable regression model. So what is that model? Yi is equal to beta naught plus beta 1 x1 I plus some variable er. Some error term will be er. And you can see it can be written as what is that? Now since I know in my data this model also can written as how it is written as yi is equal to beta naught x 0 I plus beta 1 x 1 I plus ei, right? Because this is something I am just introducing one more variable uh, where x 0 I is equal to 1 for each I, okay. Now assuming heteroscedasticity variance, that is sigma I square known, that means there is a heteroscedastic present. That means sigma I square is known. Sigma I square known. So what you have to do? You divide that equation. Let's call this equation is 1. Equation 1 by sigma I. So this means what? This means I will say that the variance of ui is equal to, or I'll say not ei, I can assume ei. Variance of ei is equal to sigma I square. Means there is a heteroscedastic variance. We have heteroscedastic variance. That means if this is known, that means the variance of ei is equal to sigma I square. So what you do? Equation 1, you divide by sigma I. What happened? Therefore, yi upon sigma I is equal to beta naught x 0 1 upon sigma I plus beta 1 x 1 I upon sigma I plus ei upon sigma I. So I divided through by sigma I. I divided through by sigma I. So now this I am expressing, therefore yi star. This is become yi star is equal to beta naught, and this I'm assuming again y naught I star plus beta 1 x I star x1 I star plus e I star. And where you know what is this all, right? This quantity become this quantity. So I'm not writing that. You can understand. Here, here, beta naught star or you may express this quantities like saying I have another estimate star like that. Okay? I have another estimate star, but the quantities of this is nothing but same. ये मेरा ये है, ये quantity मेरा ये है, ये quantity मेरा ये है और remaining quantity मेरा ये. Okay? Just understand those concepts. Here beta naught and beta 1 star are unknown. Obviously it is unknown because you need to just calculate. It is unknown parameters of the transformed model of the transformed. So when you have a model, you have obvious this beta naught and beta 1 will be your transformed model because you have transforming that beta naught to beta 1 beta 2 or beta naught and beta 1. So what happened? What about the variance? The variance, the variance of the error term of the of the transformed model is given by now see what could be the variance of transformed model. What could be variance? Ei square, Ei star. What could be their variance? This is equal to variance of Ei upon sigma I, right? What is that? I can pull out because sigma I square is constant. I can pull out into variance of Ei. But what is variance of Ei? It is sigma I square upon sigma I square, which is equal to 1. So what we found, this variance of Ei star, now it is equivalent to 1. That means your variance become constant. Therefore, this is nothing but constant. And remember, there is one of the condition we have found that your data should be homogeneous, means your variance is constant. Therefore, that is variance of the transformed disturbance disturbance term disturbance terms, I can say Ei star is constant. Means we found that the variance of disturbance term is a constant. Therefore, and you know if the variance is constant, I may apply OLS estimate. Therefore, applying OLS procedure, OLS procedure to OLS Euler's procedure to transform model which is called as weighted least square method. Weighted least square method. So this is the concept of your weighted least square method. And once you know that OLS, so we can applying OLS, and applying OLS means how to apply, and we can obtain we obtain we obtain weighted least square estimators, because we have beta 1 beta 2, that is WLS estimators, which are real. Here, so what could be your beta naught? Beta naught is equal to yi bar star minus beta 1 hat star into x bar star I. And what could be beta 1 star? Beta hat star, which is, now you are adding wi, so wi is the one term. Then we have summation wi xi yi minus summation wi xi summation wi yi whole thing divided by divided by summation wi summation wi xi square minus summation wi xi the whole square, and where this wi is equal to 1 upon sigma I square, and I bar star y bar I star is equal to, this one, this is wi upon weighted, this is your weighted mean wi and x bar I star is nothing but so this is your entire model. Let me know if you have any query. So you can read from here. from weighted least square. Yes. Tell me if you have any query related to this model. Go through once again. Take your time. Go through once again. Let me know if you have any query. Put your query on chat box. Yes, any question? Revision of today's session. What revision? Means starting from see, if you just like I'm go on reading. It has no meaning. So until unless you will write. See, because if you see have a theory part, you can understand conceptual. But that for derivation part, you must need to write it down once. Then only you will understand what is the steps, how we can, how after this step, what could be the next step like that. So just write it down once, and then if you have any query, then we can discuss. Go with the conceptual knowledge, whether what could be the like whether you can understood this steps to next step like that. Like here we divide sigma square, then we created a model, and after creating a model, this is the OLS estimators, and we found this variance. Variance is constant, so the variance is constant. So I can apply OLS. Once I apply OLS, I can able to estimate the parameters like that. So I think that is the very basic concept. So we may just go through that. If you have any questions, then we will see. So take 5 minutes break. We become fresh. Then we go to the next part, which is called multicollinearity. Okay, so take 5 minutes break, and we'll back in 5 minutes. Next concepts, which is multicollinearity. Maybe this is some term you are get familiar with the collinearity. We must have the collinear. So it's a form of linear. We talk about multi means we have more than one variable. So there maybe exist, like if you have more than one variable, then what could you multicollinearity say? So the classical regression model assumes that explanatory variables are not correlated. Are you getting the meaning? Explanatory variables are not correlated. That is, there is no collinearity among the regressor, including in the regression model. What this is, according to the Ra- Ra- Ragnar Frisch, according to Ragnar Frisch, if there is perfect or exact relationship among some or all explanatory variables, some or all explanatory variables in the model, the following conditions are satisfied. What is the condition? This is my condition. The following conditions are satisfied. So this is my condition. If this linear relationship exists among all the explanatory variables, then this is my relation. Lambda 1 x1, lambda 2 x2, so on, lambda k xk equated to 0. And what is this lambdas? Lambdas are constant. So what this says, in presence of multicollinearity, if there is presence in the multicollinearity, then what happens? If explanatory variables are interrelated, then we have this relation. Now, if you see the previous case, there will be no term of vi. There is no means there is no term of error. There is no term of error, or I can say ei or vi. So if there is no term of vi, that means I can say that there will be no multicollinearity. If error is 0, that means there will be the no presence of multicollinearity. But if you included this error term, then we must that means that the multicollinearity exists, and where vi is equal to error term. So if multicollinearity is perfect, we do not get an exact estimate of the regression coefficient, and standard error is infinite. So if the multicollinearity is perfect, I can say that we will not get the estimates of your regression coefficient. So beta naught, beta 1 will be like, right? You may not able to get that values, and variance become infinite. Variance become infinite. So if the multicollinearity is less, even even though we can estimate the regression coefficients, see it may happen the multicollinearity is there, but it is very less. It is very less. Even the estimates the regression coefficient, they possess the large standard error. So your standard error become large. Standard error become large, and that is in presence of multicollinearity, regression coefficient cannot be estimated with greater accuracy, greater precision. Means you are already knowing when you called about blue, means means there has to be the minimum variance. Then only you can call that particular estimator is blue. Otherwise, it has no meaning. And if you're talking about the large variance or infinite variance, that means uh, I can say those estimators are like it has no use. Even you can get it, but it has no meaning. So how you detect that multicollinearity? How you can detect that whether in my data multicollinearity exists or not? Okay, so that is all detections. So we can detect multicollinearity using first one R square and T ratio. R square and T ratio. Pairwise correlation T regression. VIF. VIF means variance inflation factor. So using these three criteria, one may check for multicollinearity exists or not. So first one is R square and T ratio. If R square is greater than 0.8, understand, if R square is greater than 0.5, that means it is high, then F test almost all the cases reject the hypothesis and regression coefficients are simultaneously equal to 0. Is that equal to 0? But if individual t-tests show that individual t-tests show that where I am now. But if individual t-tests show that none or very few regression coefficients are statistically different from 0, then multicollinearity exists. What do you understand by using this expression? See, if your R square value is greater than 0.8, means what you can conclude? So one may conclude that we are rejecting the hypothesis that that the regression coefficient simultaneously equal to 0. Means you are rejecting H naught, right? That is, what is your H naught? It is H naught beta 1, beta 2, beta 3, so on beta k is equal to 0. That means you are rejecting the hypothesis simultaneously beta is equal to 0. And that means the model is significant, right? That model is significant. So you are rejecting H naught, that means what? Model is significant. So if the model is significant, then one may go for t-test. That we have, I think this is the normal concept we have studied. If the model is significant, then we go for individual testing. But in individual testing, we found that none or very few regression coefficients are statistically different from 0. Statistically different from 0, right? Then multicollinearity exists. So this is one concept. This is one concept one can able to get using the criteria of R square and T ratio. But still it is not, I feel it is not good, because here one may talking about like rejecting or accepting the hypothesis. But how you can actually know whether there could be the multicollinearity exist or not. Okay. That's why there is a next criteria, pair-wise correlation between a regression. How we decide? If pairwise or zero order correlation coefficient between two regressors is high, I can say 0.8. I can say 0.8. Then regressor are collinear. Regressor are collinear. And multicollinearity exists even if the simple correlation coefficient are comparatively low. Now you know what is simple correlation coefficient. Therefore, it is sufficient condition but not necessary condition. So again, this condition fails because it is sufficient but not necessary. It may happen like for simple correlation. But if you see the third one, which is called variance inflation factor, it indicates that multicollinearity, and it is given by VIF is equal to 1 upon 1 minus R square 1 2, where R12 is the simple correlation coefficient between x1 and x2. So I've just considered x12. We can consider 2 3. We can consider 1 3 like that. It's based on the data. It's based on the data. And what is the condition? If if VIF is large, I will say greater than 10, it indicates the multicollinearity exists. It indicates the presence of multicollinearity. So I think only using the last method, only using the last conceptual knowledge, which is variance inflation factor, which is greater than 10, one may obtain in your data multicollinearity exists or not. Okay, so this method is basically VIF. That method is most suitable method as compared to previous two method, because in previous two method it may happen like it some was the like one will be not sufficient condition but not necessary condition like that. One may just explaining the model about whether it is rejected or accepted, but I think this VIF is giving the proper method which clearly says if my VIF is coming more than 10, then I can say that there exists multicollinearity or it indicates presence of multicollinearity. Okay. So what happened is there is more thing. Yeah, consequence using OLS estimator in the presence of. So what happened in the case of when the multicollinearity exists? So in presence of multicollinearity, OLS estimators, as we discussed, we have a larger variance and covariance, making precise estimation difficult. So it's become very difficult to like get the estimation become difficult. Confidence interval are much wider, leading acceptance of null hypothesis, acceptance of zero null hypothesis. You see, if you can say if the confidence interval is wider, I can say everything is belonging to the interval. Means obviously you are going to accept H naught. There will be no more criteria. And overall measures of goodness of fit are square and very high. At same time, the ratio is one or more coefficients tend to statistically insignificant. So you can say if overall goodness of it R square is very high, I think there could not be, and if that R square value can be very high, R square value is very high, is very high. At the same time, at the same time, uh, T ratio, T ratio of one or more, one or more coefficients tends to be statistically insignificant. So if you see, if your R square value is very high at that time, at that time, you can see, but still the using t test, still using t test, you may get the uh, some coefficient which is statistically insignificant. Statistically insignificant means I can say betas are equal to zero. Betas are equal to zero. Okay. And the next one is OLS estimators and their standard error can be sensitive and have a small change in the data. So that is a very important part. Like when you talk about the data, even the small data, if you change the small data in your data set, if you change the very small things, still your standard error and the estimators have very important role in your model. What else? This is the last slide. Yes, any question? Any question? Let me know question. So there are few things are remaining like plots. So we can discuss that plots maybe the next class. And then we'll go for practical based on that. Yes. Anyone having any question?